All right, little mini lecture, hopefully mini lecture in lab to cover what we're doing in lab today, which is calorimetry stuff. So heat, as you hopefully remember from Chem 20, heat is a transfer of thermal energy. This is between a system, the thing that we care about, the thing that we're looking at, and its surroundings, just everything that's around it. And this is caused by a difference in temperature. Temperature is the measure of thermal energy. So you can measure the amount of thermal energy, and we usually do this with temperature. So degrees Celsius, degrees Fahrenheit, or Kelvin. Heat is going to flow from high temperature. Heat goes from high temp into the thing that has low temperature. This is how ovens work. This is how you cook stuff. The heat is going into the thing that has the lower temperature. This will go until they reach the same temperature, which is thermal equilibrium. When the temperature is equilibrium equal. There's still going to be heat sort of transferring back and forth, but they're equal, and so there's no net transfer of heat. The way that sous vides work, the sous vide device, where you put it into hot water, or you put it into water and it just heats your meat while it's like in a bag, or whatever you put in there, you just are reaching thermal equilibrium over a long period of time. So you can cook at a relatively low temperature, and there's some benefits to that. When a system absorbs heat, absorbs thermal energy, its temperature increases by some change in temperature. So this triangle is delta. This means change in temperature. That increase is directly proportional, meaning that it's a linear relationship to the amount of heat that was absorbed. And we have a constant for that proportionality we call the heat capacity, C. And C, our heat capacity, has units of joules per degree Celsius or joules per Kelvin. This delta T is final temperature minus initial temperature. The reason that it can be either degrees Celsius or Kelvin for this delta T is because degrees Celsius and Kelvin are the same size temperature unit. So it doesn't matter which one you use, just make sure that it's the same thing. If you are converting temperature units, do it first. Do it before you calculate delta T, otherwise do not try to change it because it will be wrong. So something that I've seen some people do, they calculate this delta T with degrees Celsius and then they're like, let's turn it into Kelvin. Don't do that, you'll get the wrong number. That's not how it works. So if you're going to convert these temperature units, you want to do it first before you put it into this Q equals C delta T. Heat capacity, that C value is the heat, Q is heat, required to change the temperature, this delta T, of a system by 1 degree Celsius. We generally do not use heat capacity. The reason for this is that the larger, nope, it's not this, but the larger the heat capacity of the object, the smaller the temperature rise will be for a given amount of absorbed energy. So if it's a really big heat capacity, if it's a really large object, for example, this is actually why we don't use this. If it's a really big object, it takes a lot more heat to get the temperature to go up. Think of like if you're microwaving a small piece of food versus if you're trying to microwave, somehow you can fit a turkey in your oven, your microwave oven. It's going to take forever to microwave a turkey because it's so much bigger. The heat capacity, C, depends on the amount of matter, usually measured by mass, which makes it an extensive property, and that's annoying. We don't like doing that because then the heat capacity is different for every single object, and that's not very helpful to us. It doesn't apply to other situations, the reason we don't use that. So instead, we use specific heat capacity. The specific part, specifically, 1 gram of the substance. So instead of using heat capacity, we use specific heat capacity, and so this is setting our amount as 1 gram. So we can use this to scale up or down our heat capacity depending on how much we have. So for heat capacity, if we have a small chunk of copper and a big chunk of copper, they're going to have different heat capacities. However, if they're both copper, they're going to have the same specific heat capacity, so we can use that same number for both amounts. That's the reason that we use that instead. So specific heat capacity, the amount of heat, Q, in joules, usually, needed to raise the temperature of 1 gram of that substance by 1 degree Celsius. And this is always going to have units of joules per gram degree Celsius. Technically, it could also be Kelvin, because of what we talked about before, the delta T, degrees Celsius and Kelvin are the same size for a delta T. We can also do a molar heat capacity. So this is per 1 mole of a substance instead of per 1 gram of a substance. We typically are not going to use molar heat capacity. Specific heat capacity is what we're going to use most of the time. The way that we're going to use these intensive properties is with this formula. So this formula is sometimes called MCAT. Because the delta here kind of looks like a capital A. So you'll often hear this Q equals MCAT, not to be confused with the test you take before you go to med school. So sometimes you'll hear it called Q equals MCAT. Q is heat, typically in joules. Our C sub S is our specific heat capacity. And you typically look up the specific heat capacity in a table like this table 7.4 from our book. And then as a reminder, this delta T, our change in temperature, is TF minus TI, our final temperature minus our initial temperature. Delta T can be negative. It will sometimes be negative. If it's negative, that just means the temperature went down instead of the temperature going up. Water absorbs a lot of heat, or can absorb a lot of heat because of its high specific heat capacity, a value of 4.18, which is really large. Most of the metals are under 1. Some of the things that conduct really well are like this 0.128, very conductive in terms of heat. Water has a really high heat capacity, so it takes a lot of energy for it to raise or lower its temperature. So areas like San Francisco that are surrounded by large bodies of cold water, that large body of cold water can absorb a lot of heat out of the air, so it keeps the surrounding air relatively cool. Water is commonly used as a coolant. Like in AI, they're using a lot of water to cool down their things because it can absorb a lot of heat and it's relatively abundant. Water and antifreeze is also used as a coolant system in most vehicles, internal combustion engines especially. Here's an example of a problem that we might do with Q equals MCAT. To determine whether a shiny gold-colored rock is actually gold, a chemistry student decides to measure its heat capacity. She first weighs the rock and finds it has a mass of 4.7 grams. So mass equals 4.7 grams. She then finds that when it absorbs 57.2 joules of heat, so this is going to be our Q, the temperature rises from 25 degrees Celsius to 57 degrees Celsius. So this from is letting us know that the initial temperature is 25, and then the to is letting us know that the 57 degrees Celsius is our final temperature. So T sub F is 57, and T sub I equals 25 degrees Celsius. We want to find specific heat capacity and determine whether it's consistent with the rock being pure gold. So Q equals MC delta T equals TF minus TI. Let's calculate our delta T first. We're going to do 57 minus 25, which is 32 degrees Celsius. We are calculating specific heat capacity, so we'd have to do a little bit of algebra to get C by itself. When we do that, and flipping it left to right, CS equals Q over M delta T. So we plug in joules, put that over grams, and delta T with degrees Celsius. We get a value of 0.38, and the units are joules over grams degrees Celsius. Nothing canceled out. Questions about that solve? So that's the specific heat capacity, and then we want to figure out, is that value consistent with the rock being pure gold? So we'd go back and reference our table. Gold has a value of 0.128, and this has 0.38. So this is not pure gold. Might not even have any gold in it at all, but it's definitely not pure gold because the C value doesn't match the C value for gold. We can also do questions like this where we have a temperature change. We've got a 55-gram aluminum block initially at 25 degrees Celsius. It absorbs 725 joules of heat. What's the final temperature? So using Q equals MCAT, and knowing that delta T equals TF minus TI, what we're looking for is the final temperature, or TF. So there's a couple of ways that we can solve this. One of the ways is that we can solve for delta T, and then after that solve for TF. Or you can plug in this TF minus TI in the place of delta T and rearrange the whole thing to solve for TF by itself. I think that's the more advanced way to do it. If you feel comfortable doing that kind of algebra, go for it. I think solving for delta T by itself first is the way to go. To solve for delta T, we need Q. Do we have Q? We do have Q. Q is 725 joules. We also need M. Do we have M? Yes, we have M. M is 55.0 grams. That's our mass. We would also need C. Do we have C? We do not have C. Where could we find C? In the alphabet, it's the third letter. But more important to our question, we can find C from looking it up in a table. So we would go back to our table or look it up, or on an exam we would be given the C value, We were told that it's aluminum, our C value 0.903. With units joules per gram degrees Celsius. Now that we have everything except for delta T, we can find delta T. So rearranging, delta T equals Q over M CS. So plug in 725 joules, divide by 55 grams, and also 0.903 joules over grams degrees Celsius. The way that the units cancel out, we've got joules on the bottom. It's on the top in our C units. That's going to cancel out with the joules on top. So those joules cancel. We've got grams on the bottom, and we've got grams double on the bottom. It's on the bottom of the bottom. Those also cancel out. The delta C, sorry, the degrees C is double on the bottom. That flips to the top. I don't know what I'm drawing there. Arrow. Degree C. So degree C is on the top. Plug the numbers in. 725 divided by 55 divided by 0.903. And we get 14.597 ... degrees Celsius for delta T. So we've got our delta T. We're finding TF. We were given a TI. That's the 27.5 degrees Celsius. So rearrange for TF. TF equals delta T plus TI. So add 27.5 to the answer we got from the previous problem. In this previous problem, we had 3 sig figs for each of our terms, which is the same as 1 decimal place when we're switching to addition. Both of these have 1 decimal place, so we expect 1 decimal place in our final answer. 42.09 and some other stuff. The 9 tells us that we round up. So 42.1 degrees Celsius is our final temperature. Questions or concerns with how we got that number? All right. So if you take 2 objects at different temperatures and you put them in contact, heat will flow from the material with the higher temperature to the material with low temperature. This is something that we inherently know. If you touch a hot pot, the pot is hot, so it transfers heat into your hands and you get burned, depending on how hot it is. Heat will flow until both materials reach the same final temperature. The hot object cools because it's losing heat. The cold object heats up. It absorbs heat. And assuming that we're working in a perfect environment, which we're always going to assume, at least on exams, the amount of heat energy lost by the hot material is the same as the amount of heat gained by the cold material. The energy is conserved. So the amount of heat that's lost by one thing is the amount of heat that's gained by the other thing. The way that we would write this out is that the heat of the system the amount of energy that was gained by the system, added into the system, is the same as the amount of heat that was lost by the surroundings. So it flowed heat flowed from the surroundings into the system. Energy into the system, lost by the surroundings. All this is doing is saying that we didn't lose any heat somewhere along the way. We're not doing like a friction thing like we might do in physics, where some of our energy is lost as friction or heat or whatever. We can apply this to things like adding a block of metal to water, so calorimetry stuff. We're going to be doing something like this today. Taking a block of metal at 55 degrees Celsius and adding it to water at 25 degrees Celsius. Which is hotter, the metal or the water? The metal's hotter. Since the metal's hotter, energy is going to flow from the metal into the water. So we've got the metal in the water. The energy flows from the metal to the water. So the metal loses some energy, and it's equal to the opposite of whatever the water gains. And the temperature that they end up with depends on a couple of factors. How much metal and water we have, and also the specific heat capacities. So from the Q metal equals negative Q water, just saying that they're opposite, the amount of energy that the metal lost is the opposite of the energy that the water gained. You can plug in MC delta T for both of those. If you plug in the masses and the C values, you can eventually solve for delta T. You can figure out what the final temperature was supposed to be. And you should have done a lab like this in Chem 20, where you like mix two water samples together, hot water and cold water, and you figure out what the final temperature was supposed to be. That might look something like, I think this is that question. A block of copper which I believe has a C value of 0.385 joules per gram degree Celsius, of an unknown mass, has an initial temperature. The copper is immersed in a beaker containing this much water at a temperature. The final temperature is 24.2 degrees Celsius. What's the mass of the copper block? We want to label all of our variables because it's very easy to lose track of our variables. We've got copper and we've got water, and we need to label these things. Our copper has an initial temperature of 65.4 degrees Celsius. So our initial temperature of the copper, 65.4 degrees Celsius. So the little I here is for initial, the comma Cu is for copper. So this is our temperature for the copper. You don't have to label it this way, but this is the very mathy way of doing it. This is how you'd typically see it. The copper is put into a beaker. It's got some water. I'm going to write MW, mass water, 95.7 grams. It's also got an initial temperature. So T sub I comma W for water, 22.7 degrees Celsius. They share the same final temperature. And we're looking for mass of the copper. We would also need our C values. That's why I wrote the C value. I think this is for copper. And then for water, 4.18 is what showed up in our table. It's almost more of an algebra problem than it is really a chemistry problem. And then the one extra piece of information that we need to crack this open, our copper starts at a higher temperature, the water starts at a lower temperature. We're mixing the two of them together. How does the energy transfer? It's going from the copper to the water, and we're going to ignore the surroundings because it makes things very convenient for us. The copper is losing some energy. The heat of the copper is going to be some negative sign. It doesn't matter which side the negative is really on, but the Q copper is going to be a negative, and that's going to be equal to the amount of heat that the water gains. So we're setting these two as opposites to each other, and there's a negative sign. So the heat that's lost by the copper is going into the water. And then we do this substitution. So we sub in mc delta T, negative mc delta T. So in this case, the Q copper part is going to be the negative side. So negative mc delta T. If you don't get this negative in here, you're going to get a crazy answer. So negative m c delta T equals m c delta T. And to help us keep things straight, we're going to label them all with their sub Cu and their sub W. And then we get to do a whole lot of plug-in numbers in. Let's go ahead and calculate our delta T's first. It's going to be temperature final minus temperature initial. So our delta T for the copper, 24.2 degrees Celsius minus 65.4 degrees Celsius. Our delta T for the water is equal to 24.2 degrees Celsius because that's our final temperature, minus the initial temperature of the water, 22.7 degrees Celsius. I'm rushing to try to give us the most lab time as possible. So those are our delta T values. For significant figures purposes, I'm pointing out we've got 1.5 degrees Celsius here. We went from having 3 sig figs each to having 2 sig figs. Because of the subtraction, we care about decimal places, 1 decimal place. But this is also just 2 sig figs, which will become relevant for finding our final answer. So now we've got delta T of copper, delta T of water. We can solve for our mass of copper. And I know it's probably, this is the most confusing way to do it, to just do it all in one step, but I'm going to do it all in one step. Big negative out in front because we'll have to multiply by this negative at some point. We're going to have the whole right side, the mc delta T for water, over the c delta T of copper. and you should get a value 37.8 ... grams, rounding for 2 sig figs, 38 grams of copper. Questions? All right, yeah.
The negative sign, when you distribute it, is it to all of the variables like mass, the temperature?
You can just do everything inside and then multiply it by negative at the end. If you do everything inside, you should get negative this number, and then it just turns into a positive. You can't have a negative mass. Would be the other way that you could figure out flipping it. Okay, 2 types of work that we're going to talk about. I think they're relevant for the critical thinking questions. There's also some more calculation stuff that's relevant for the lab. When a force causes a change in volume against an external pressure, this is called pressure volume work, or PV work. PV work is important. When gases expand, there's a change in volume. So expanding means that their volume is increasing. When their volume is increasing, they have to push out the outside whatever's there. So in that expansion, that act of expanding, they're pushing on the outside atmosphere, and that is some work. So our delta V is positive, but the system is doing work on the surroundings. It's expanding, so it's exerting work, and so that would be a negative value for work. So the work of the gas is negative, and so we would have this work equals negative P delta V. So whatever the external pressure is times the change in volume, usually in liters. You can also convert with joules. This is the conversion factor for that. I don't think this shows up on your yellow sheet. You probably have to use it on the homework. You'll definitely have to use it on exam 3 when I give you a pressure volume work question. These problems are relatively simple as long as you have this W equals negative P delta V, which I think I usually give on exams. Let's look at an example problem with this. So copying over all the important information from the previous slide, excluding the external part for our pressure. A cylinder equipped with a piston expands against an external pressure. The external pressure is 1.58 atmospheres. So P equals 1.58 atm. The initial volume is given, the final volume is given. And we want to know work in joules. That's the wrong color. Work in joules. What is delta V? What does the delta stand for? Change in volume. So delta V is our change in volume. There's also a formula for delta V. It's the same idea as our delta T. So delta V is V final minus V initial. We are told our initial volume and our final volume, so we can plug those in here and calculate our delta V. Final volume 1.245 liters minus initial volume 0.485 liters. Our change is 0.760 liters. This is a positive number for our delta V. This means that it expanded. And it expanded by 0.76 liters. So to find the work that was done, we plug in negative P delta V. So negative 1.58 atmospheres times 0.760 liters. What do our units turn into? What units do we have? We have liters atmospheres. We didn't have anything that canceled out. We were asked for work in joules, and so that's where this conversion factor comes in. 101.3 joules equals 1 liter atmosphere. This is a conversion factor. We have liters atmospheres, so when we make the conversion factor with this, joules will be on the top, liters atmospheres will be on the bottom. Here's what that looks like. So 101.3 joules on the top, 1 liter atmosphere on the bottom. Liters atmospheres cancel. And we get negative 121.6 ... joules. Round it to negative 122 joules. How much work was done by the system to expand? How much work did it do on the surroundings? Is it negative 122 joules? Is it positive 122 joules? The system did 122 joules of work. Because of the way that it's worded, it gets flipped. It used 122 joules. The negative is just saying that that's what it did. It's very fun and confusing and not at all confusing. I would maybe give you full points if you answered negative 122 joules, if this was on an exam. We haven't done delta E stuff. I'm going to skip this as well so that we can talk about constant volume calorimetry. Actually, I'm going to skip to this one, to this one. This is the last slide that's relevant for today's lab, and maybe we'll come through and brush up on some of this other stuff. So there's pressure volume work where a system expands and it does some work. It loses energy because it's doing some of that work. You can also do constant volume calorimetry. In constant volume calorimetry, you use what's called a bomb calorimeter. And this is a sealed container that cannot expand. Because it cannot expand, you don't lose any energy as pressure volume work. It doesn't lose any energy as expansion, and so all of the energy that's produced, all of the energy that's transferred, is transferred as heat. There's no work being done as well. And there's a calorimeter constant for a bomb calorimeter. We are going to calculate a calorimeter constant for our calorimeters. Our calorimeters are just going to be styrofoam cups. The calorimeter constant is the heat capacity of the calorimeter. It's usually calculated just for that calorimeter. And so this uses heat capacity, not specific heat capacity. It's just for that one calorimeter. So if no heat escapes, the heat gained by the calorimeter equals the heat released by the reaction. So we've got this equation. The energy gained by the calorimeter equals the calorimeter constant times the change in temperature. We can calculate a calorimeter constant if we know how much heat was lost, if we know what the change in temperature was. So for our lab, we're going to be adding water into our calorimeter, 2 amounts of water into our calorimeter. We know what the final temperature is supposed to be because we can calculate it. Any of that heat that's lost, we're going to assume was gained by our calorimeter. So we can calculate our C value for our calorimeter, which is going to be helpful for the rest of our lab. That's kind of the only part on here that's relevant. Questions? We'll come back and look at these slides again at some point. I don't know if that's next class or next lecture, but at some point.